gas chromatography. It's one of those backbone techniques in the analytical lab, and if you work with volatile samples, you probably rely on it a lot. But how does it really work? Let's break it down, step by step. First, the principle. Gas chromatography, or GC, separates compounds based on how they interact with a stationary phase inside a column, while being pushed along by an inert carrier gas. Think of it like a race. Each compound runs through the column at its own pace, depending on how much it likes to stick to the stationary phase versus how much it prefers to hang out in the gas phase. The more a compound interacts with the stationary phase, the longer it takes to reach the finish line. That's your detector. Now, on to the instrumentation. GC systems have a few key parts. There's the carrier gas, usually helium or nitrogen, that sweeps your sample through the system. You inject your tiny liquid sample into a heated injector port where it vaporizes instantly. Remember, your sample needs to be thermally stable. Next, the vaporized sample enters the column. Columns can be packed or capillary, and they're housed inside an oven because temperature control is everything in GC. The temperature program can be constant or ramped, depending on what you're analyzing. As the separated compounds exit the column, the detector picks them up. Flame ionization detectors and thermal conductivity detectors are among the most common. Each detector has its own strengths, depending on what you're looking for. Let's talk applications, because GC is everywhere. In environmental labs, it's used to track pollutants like pesticides or volatile organics. Pharmaceutical labs use it to verify purity and check for residual solvents in drugs. Food and beverage labs rely on GC for flavor and fragrance analysis. Think of how a tiny change in a compound can totally change the taste of coffee or the aroma of wine. And in forensics, GC is indispensable for analyzing toxins, accelerants, and even blood alcohol content. Why is GC so popular? It's fast, highly sensitive, and incredibly specific. If your compound can be vaporized without breaking down, GC will probably separate it for you. But there are limitations. Non-volatile or thermally unstable compounds aren't suited to gas chromatography. For those, you'll need a different technique. So next time you run a GC sample, take a moment to appreciate the complexity behind those clean, sharp peaks. It's a technique that's been refined for decades, and it's still one of the best tools for separating and analyzing volatile compounds. Thanks for watching. Stay curious and keep pushing the boundaries of what your lab can discover.